let's put down what the drain source and all that is. Okay, what's the drain for the NMOS transistor? V0, right? Source is ground. PMOS transistor, drain is, basically the source has to be fixed, should not change when the input is changing, right? Only then your gate overdrive will always be as good as it can be, right? So therefore the source for the PMOS has to be VDD, source for the NMOS has to be ground. Okay, so this, this logic gate has some constraints. When this input goes from 0 to VDD and the output falls like this, there is one constraint that is always maintained in this logic gate. What is that constraint? Okay, so let's now list, now let's list out these conditions and then I think you'll get it after that. So let us look at VGS and VDS for the NMOS and PMOS. Okay, the input to the gates are V in, the output at the drain of both these transistors is V out. So what is VGS of the NMOS transistor? It is V in. VDS, V out. What about PMOS? V in minus VDD. VDS is, be careful, it is V out minus VDD. VDS. Now there is some VGS, some VDS on the NMOS, some VGS, VDS on the PMOS. What should happen to these two currents? At all times, they both have to be equal in magnitude. Okay, remember that the current in always will flow from supply to ground like this. When the current can flow, that is assuming that one transistor is allowing conduction, right? For example, if the NMOS is off and can allow no current, then there can be no current in the PMOS as well, right? It's in series. So the constraint that is going to be imposed is IDSN, NMOS current. Remember, the direction for IDSN is like this, IDSN. What's the direction for the PMOS current? No, IDS direction. It has to go from here, like this is IDSP. So therefore IDSN should be equal to minus IDSP. This will hold at all times, okay, for all t. Okay, so now assuming that the transistor is ideal, suppose the input were 0, what is IDSN? It's an ideal transistor, input is 0, what is IDSN? 0, right? Therefore the current through the PMOS also has to be 0, right? Which means that the drain voltage will adjust itself so that you get this 0 current happening appropriately. Okay, so let us look at that. Suppose if V in equals 0 implies VGSN is how much? VGSN is 0. This implies IDSN equals 0 because it is less than VT. Okay. Now, what is the VDS on the PMOS such that the drain current to the PMOS can also be 0? You get my point, right? If because of this constraint, my VDS on the PMOS transistor should adjust itself so that the current is 0. VDS equal to, exactly, this implies VDSP should also be 0, right? Now this implies IDSP should be 0, right? Therefore VDSP should be 0. So if VDSP should be 0, it implies V in minus VDD equal to 0, and I mean V out, I'm sorry, V out equals VDD. Clear? This is a more rigorous analysis of the same thing that we just discussed, where the input is low, output will be high, because these currents have to match. Similarly, if V in equals VDD implies, what is VGSP? What is this? V in minus VDD, right? Equals 0, right? And obviously this is greater than VTP. Remember, VTP is a negative number. It should be less negative than that, only then it can happen, or it should be more negative than that, only then it can conduct. Therefore, IDSP should be equal to 0, which implies that IDSN also has to be 0, and therefore, what is the only way this can happen? The drain source voltage of the NMOS transistor should be 0, okay. So therefore, V out, I'll write that step, VDSN equal to 0 implies V out equals 0. Any questions here? Okay, so this are the extremes that we analyzed, okay. The idea of doing a voltage transfer characteristic is to sweep V in from 0 to VDD and then analyze what will happen to V out in the process by applying exactly these constraints. What will happen is, as you sweep V in from 0 to VDD, for each value of V in, right, V out will adjust itself so that the current in both NMOS and PMOS will be the same. Okay, so that leads us, much time do I have? Enough time. Voltage transfer characteristics, VTC. Okay, so first we will look at this intuitively and figure out what should happen, and then we will look at the more rigorous way of identifying these points on the VTC. Okay, first we look at the intuition. So we are going to plot V out versus V in, okay, for my CMOS inverter. V in, V out, right? And of course the constraints are simple. VGSN equal to V in, VDSN equals V out, VGSP equals V in minus VDD, VDSP equals V out minus VDD, and IDSN equals minus IDSP. Okay, so what we are going to do now is to sweep V in from 0 to VDD. In the process, there are going to be some transition points, right? So when we sweep V in from 0 to VDD, what do you think the first point of transition will be? So when V in equal to 0, what is the state of the NMOS transistor? Off. At what point? Of course, if I increase the gate voltage to VDD, NMOS will turn on. So somewhere in between it's turning on. What is that point? VTN, it has to turn on, right? So therefore, this is going to be my VDD. The first point of interest is VTN. For an ideal transistor where leakage current is 0, output has to be what? Until I reach VTN, has to be VDD, because the VDS of that PMOS has to be 0 and therefore the thing has to be VDD, right? If there is some finite amount of leakage current, however small it is, then VDS has to allow that much current to flow through the PMOS transistor. So VDS will be slightly lower than VDD, right? This is in the ideal case, but for now let's look at the real case. Okay, so I am going to consider this. Output will start at VDD. Now the NMOS transistor is turning on. As soon as I cross that VTN, it is turning on. In what region of operation will my NMOS transistor be? Saturation, you agree? Why? Because VGS is how much? VGS is just just slightly above VTN. So VGS minus VT, a very small number, but Vout is nearly VDD. So therefore the NMOS will turn on in saturation. This is the first point that we have to observe. NMOS turns on in saturation. Okay. Now, what about the PMOS transistor in that region? Why linear? Actually, tell me, even before, suppose Vin is less than VTN, which region of operation will the PMOS transistor be in? It will be in the linear region of, because it has to depend on VDS, VDS has to be 0, right? So therefore it's in that linear region of, so the PMOS will turn on at the same time PMOS is linear region, right? And of course now current is going to flow because both NMOS and PMOS are on, right? One in saturation, other in linear respectively. Therefore the Vout will adjust itself slightly lower than VDD, right? So the Vout will now start falling. At some point the PMOS transistor will come out of this linear region and get into saturation or velocity saturation. You agree with me? Why is that? What is happening to the VDS of the PMOS transistor in that period? Or what is happening to mod VDS? It is increasing, right? And therefore the VDS at some point, VDSP, mod VDSP will exceed VGS minus VT of the PMOS, and therefore that will get into the saturation region at some point, and this will happen somewhere near VDD by 2. Okay, so there will be one point in which both NMOS and PMOS transistor will be in saturation region. Okay, so this will continue to happen. Now at what point will my PMOS go off? So for that, what is my VGSP? So VGSP should be less than VTP, less than VTP, only then it can turn on. VTP is a negative number, again let me remind you again and again, which implies Vin minus VDD should be less than VTP, right? Only then it can turn on, which implies when V in should be less than VDD plus VTP. So this point is not VDD minus VTP, or if you want to say VDD minus, then you say VDD minus mod VTP. So this point is going to be where the PMOS transistor turns off, is VDD plus VTP. Okay, and this will come all the way down here, and then of course the output will be absolutely 0 after that. Why? Because now it's an ideal transistor. PMOS transistor cannot tolerate any more current. Therefore, what should happen to the VDS of the NMOS transistor? 0. Okay. Now, in this region, when the PMOS is off, what region of operation is my NMOS in? It is in linear region. So here PMOS is off, NMOS is linear. Out here NMOS is off, PMOS is what? Linear. Now, like I said, there is one small region where both here both N and P will be in saturation. Okay, saturation or velocity saturation depends on whether you are talking about a long channel device or a short channel device. The region before that, here, what will be my NMOS state, PMOS state again? N is saturation, PMOS in linear, and the exact opposite will happen in this region where NMOS is in linear, PMOS is in saturation. Okay, so there are like how many regions? Region 1, 2, 3, 4 and 5. There are 5 regions that the voltage transfer characteristic goes through, and you should be able to explain each one of them correctly. Okay, so we will look at primarily this region 3 will be of very much of importance to us, because that's where the sort of the trip point that I spoke about occurs. Okay, so this is the V in, V out versus V in of our actual inverter. What was the VTC that we wanted of an ideal inverter? Sharp line, right? We wanted the ideal VTC to be something like this. Basically up to this point it will be VDD and then it will just drop thing. So this was ideal VTC. Okay, so clearly right here you see that there is a region or a range of input values which are treated as logic low, which means the output will be logic high, right? Similarly, there is a range of input which will be treated as logic high, the output will be logic low, no problem. But there is an indeterminate region in between which is neither logic 0 nor logic high. I will tell you why. It's, I'll show you why that happens, and this is of primary importance to us because this is where the input should not go and land. Okay, if it does land, then the output becomes a random value dependent on noise. Okay, we'll come to this later, but for now I am just giving you the intuitive picture of how the voltage transfer characteristic is different from the ideal VTC that we wanted.